Thank you very much for inviting me, having me here. Happy to be here, happy to be in person. I'm really, it's a great place and a great audience. I'm really very happy. So I'm going to talk about a subject. Actually, I did give very similar talk not long ago at the Georgi Center and remotely. And so this is about pressure and singularities. And I also gave something similar to the meeting in Cambridge, again remotely. And I will mention some connections with turbulence a little bit. In my abstract, I put just one sentence. The talk you will see is not so much about turbulence, but I will make a little advert, as they would say in English. So, and I wanted to give a Blackboard talk, but I think that I want to bother you more, so I have more things to do. So maybe I'll slow down in the beginning, maybe I'll slow down again. There's a Blackboard. So some of you might know these equations called Navier, Stokes, and Euler. People who came at this workshop for not for the lunches might know. And the gradient of the pressure is the driver. So I used to several times say everything is the vorticity, everything is the stretching, everything is the transport, everything is the pressure. So today everything is the pressure. So in this talk, I'm going to talk about bounds on pressure, implied regularity. So maybe to this audience, I don't need to motivate, but I will motivate anyway why we care. So K stands for Kolmogorov and turbulence stands for turbulence. Now, some of you may not need to be told this, but turbulence is a fundamental scientific problem. So maybe for some of you, it needs to be told. It's a fundamental scientific problem, not only to fluids. So it is a fundamental problem for plasma. There is a fundamental problem for astrophysics. There is a fundamental problem for even, let's say, some things that have to do with large-scale circulation, ocean and atmosphere. So I'm reminding here about some objects that are defined, or rather they're not defined. There are these funny braces here, which are either ensemble averages or invariant measures or space-time averages. The reality of it is that some of these results, and the Kolmogorov spectrum is coming here, are verified, let me put it down, in enormously many situations, in enormously different environments, from compressible Navier-Stokes, computed compressible Navier-Stokes, slightly compressible, computed on the largest machine that was at that time, and this was some time ago, maybe 10 years ago, to atmospheric science. So the fact that Kolmogorov spectrum is k to minus 5/3 multiplied by a number that's independent of viscosity is an amazing fact of life. It's not an amusement, and it's proved by dimensional analysis. So this is a rate of, it's an energy per wave number, and it's done at the level of, let's say, very elementary, let's not call it high school algebra, because I don't know what people learn in high school anymore. But so the statements are universal statements, not because somebody wants them to be universal, but because they are found. And therefore, we need to take them as mathematicians very seriously as inputs. So the rate of dissipation on this slide and in the previous slide, maybe I should go back to Navier-Stokes a little bit. Navier-Stokes, in this particular discussion, there is no force, and it is really reflecting an equation with mean zero. So this is fluctuations around the mean, and for simplicity, we took the mean to be zero. So if you have no force and it's Navier-Stokes, you know what will happen. The thing will go to zero, okay? Maybe in between it will blow up and you can go to the bank and get $1 million if you know how to prove that, but it will go to zero. And if you put a force, then it will go to a permanent regime. The permanent regime might be a finite dimensional attractor or something simpler, a steady solution, depending on the situation, but you know that it will go to a permanent regime. So it is, a lot of this can be dismissed as being studying a situation that is rather easily understood. On the other hand, the fact that you have a restoration of translation invariance, some law connecting translation to turbulence, completely non-trivial. Because you are dealing here with nonlinear transformations of space, and you are saying that you do experimental observations and you get a law under maybe space and time averages. In the reality, experiments record things in various ways. They do either a Taylor hypothesis and do time measurements, or they actually have some visualization methods or spectral methods. And the fact that you get restoring of a translation law is an amazing thing. And again, the parameter is epsilon. So this epsilon is supposed to be non-vanishing, the limit of Reynolds number. So there is an inertial range in which this happens, meaning there is a mystery of what happens for smaller scales. Normally, most physicists believe that at the smaller scales, things become boring, smooth. In other words, this exponent will be 2 if you go down to the smaller scales after some transition. So there are other people who believe that there is injection of some sort of a non-smoothness at all scales, and this is not clear. But most of traditional people in turbulence believe that below the dissipation scale in K, so for larger K than KD, or the behavior here is exponentially decaying. So it's a very fast decay of the K. So there is also a 4/5 law, which I wrote here in terms of absolute value. So there are more refined differences between them. There is a 4/5 law that says the third order, more longitudinal moment is linear. And I wrote here in absolute value, this is, these are called structure functions. If you put the absolute value in there, have various things. So for us, this is a very ambitious question. It's not only for us, it's also for physicists to find the correct framework validating and predicting a numerical evidence, and universality, which means in inertial language, which means exactly what we have seen, a procedure by which you extract information from solutions of Navier-Stokes equations and match them to experiment. So there are, in addition to the Kolmogorov laws, there are significant intermittency corrections observed numerically, and there are theories about them. And these, the degree to which you trust them becomes a little smaller and smaller as you raise this power of P because of statistical issues, if it's numerics, or in experiments also because of scale issues. But typically, the statements are that the structure functions of order P scale with an exponent zeta P that is not exactly the Kolmogorov exponent, but it is diminished as P goes above 3. And this diminishing can be drastic according to the the current beliefs pretty significant. So at the end of the day, you erase all growth. And the displacement is almost like you shock, almost like you are obtaining discontinuity, or maybe you get only logarithmic moduli of continuity. So those are all at this point either speculations or matching some numerical observations of people. So the main point about this is that in particular, for instance, for lower p's, that's the departure is, so in other words, the departure is going down. So for p equals 3 is exact supposedly. So for p equals 3, you get 1. And then for lower p's, you might get larger than, for instance, the corresponding value at 2 would be 2/3. You would get larger than 2/3 experimentally, apparently significantly larger. And that will have some consequence for us, even for us today. So this is the background, but I want to insist that this is not something that only some theoretical physicists are playing with. So it has consequences. So Reynolds number going to infinity, I forgot to say that, but this is essentially all this theory is valid in the limit of a Reynolds number going to infinity. Reynolds number definition is also an issue. So for us, if the theory in the most, let's say, generous way you can imagine it, is that it doesn't matter how you define the Reynolds number as long as it's a good physical definition, the scale of your pipe, and that's your L, and the inflow velocity, and the kinematic viscosity, and you're done. But the reality is that if you're solving Navier-Stokes equations, there are many ways of trying to define a Reynolds number, and we don't know really what is the most convenient. In particular, some of these statements, there is something called refined self-similarity, in which the cutoffs depend on norm of the solutions. So what's the math? The pressure equation is solving a Poisson. So it's Laplace P minus Laplace P is u dot grad u, divergence of u dot group. And you can use incompressibility to pull out the derivative. So then you can write this in various ways. And the pressure is defined up to a free, possibly time-dependent harmonic function. It's the same equation if you have viscosity, and it's the same equation if you have hyperviscosity. And it's the same equation if you have compressible MHS, which is actually Euler. So it's the same equation for plasma in steady solutions. So it behooves us to understand it. And it's a thing that I like very much Tarek's talk. So we know a little bit about the Laplacian, he said. So I like that. We know a little bit about the Laplacian, so we can think that we could know a little bit about this pressure, and there are a few things we do know. So a representative, so if you think that the velocity goes to 0 at infinity in the whole space, and I divide by the Laplacian, then I get this product of Riesz transforms, and I will refer to this one as the standard representative in the whole space, and this is, it's legitimate. And there can be still mysteries, but not today. So I wanted to mention this. I'm not going to use this, but it's a well-known result. I think that Phil published it. I don't know if Louis published it. Actually, I know he knew it, but I don't know if he published it. And it's the following, that the pressure is twice as regular as the velocity in a smaller range. So if alpha is less than 1/2, and let's forget about the time. This is really about the Laplace equation. Then the pressure is in 2 alpha. And if alpha is 1/2, you end up in logarithmically close to Lipschitz. And if alpha is larger than 1/2, then you're Lipschitz. So it's an elementary thing. This, however, the way I do it, it will be related to what I'm going to bother you with a little later. This is not the only way to measure partial regularity of the pressure. So it might be useful for other contexts as well. So I'm going to remind, this is a talk about things you know. So I'm going to remind some of them to you. And I want, before, maybe let me not put this slide yet up and remind you a little bit about turbulence. So here, one of the ways of thinking of this is space-time averaging. So in particular, you would say that what you are doing here, you are looking at fluctuations. So U equals 0 is the mean. You are looking at the fluctuations, but you are looking at time averages of the fluctuations and space averages. So there is a smoothing involved. As long as you are a mathematician, you know, every time you integrate, you're gaining some. So let me remind you some things you knew before I put results, that other things that you knew. So one thing that you knew is that, for instance, if I take the time average from someplace of the velocity, this belongs to H3 halves for weak solutions of Navier-Stokes. Another thing that you probably knew is that if I take I don't like Laplace. I'm going to write A, of course, is the Stokes operator. So you knew this. I mean, we knew this. And an easy one, as people are so this is maybe in the book with Foyash already, but if you don't want bounded, so this is in bounded domains, you can take, you can write one of these I alphas This is in 3 dimensions, by the way. Right, so you take a Riesz integral, which is minus Laplacian to the, so alpha is 1/2 is what we have there. And I alpha takes you from H3 halves to N3. And if you know this, you know how to prove this, okay, in the whole space. So, right, everybody knew this. The way you prove this one, if you believe this, you multiply by A1/4. The equation, so the Navier-Stokes equation looks a little bit like this. Huh?
You mean L3 to H3 halves? Isn't it smoother?
The I alpha is the inverse. Yes. Well, this is minus Laplacian minus Laplacian. Okay. So yes. Thank you. I shouldn't give a Blackboard talk after not sleeping at night. So, all right. So you multiply by A1/4, this one, and now you know that this guy is going to be time integrable. And therefore, you have A minus 1/4 U. Well, let's A minus 1/4. Let's call this guy V. I should call it U bar. It's a time active. So you get A minus 1/4 U bar plus A 3/4 U bar plus A minus 1/4 this one belongs to L1 of L2. So you multiply by A 3/4 U bar and you're done. Okay, you get this information that A 3/4 U bar. Okay. Sorry. Probably messed it up a little bit. It doesn't matter. So what I'm saying now is that it is actually known more. So the average is more regular. I messed it up a little bit, I think, but what I meant was that we know that the average, if you look at the first line, this is Giopé-Temam, tells you the time average. If you take here the m for which this number is 1, that m is 3/2. So the time average at power 1 in 3/2 is 5. That's just V bar or U bar belonging to H 3/2. Okay, so that's actually stronger because U bar being in H 3/2 is the norm after I take the time average, and here I can take the time average of the norm. Okay, so we knew this, and we know as a consequence of this that the H1/2 is bounded of 3/2, and that's L3. So I actually, that the whole, I think I messed up there. It's a very elementary thing that I messed up. So anyway, we know also this one. And this is an important quantity. So there are lots of people that study these equations, and I think there are several important known informations about it. So among the ones that I will emphasize today is the integral in L3 of the gradient that is significant. And there are others, the fact that the ballistic length that you can send an object is finite. So far you can throw something is finite, this is the length. And also that there are if you take here m equals 2, you get 2/3. So that's below 1. So the integral in H2, the Laplacian, is integrable to a power less than 1. But there are integrals of the Laplacian to powers larger than 1 that are finite. They are obtained by looking at the vorticity. So that's a Lorentz space. So this is a little more recent result, having it in Lorentz spaces all the way, but not quite to infinity. So the sufficient conditions that you also knew are in terms of, let's say, L infinity or L3 and anything between, but they're a little different. So the conditions up to P equals 3 are conditions that imply quantitative bounds and are quantitative in a strong way. This one, which is been done by Skoriaza, Serogin, and Shverov, is a little more delicate, and it doesn't give you the same kind of straightforward quantitative estimates. So but that's a very important quantity, and I'm going to come back to this. So if you look at the dimensions of this thing, this has dimensions of viscosity. So it's non-dimensional in some language. In terms of the pressure, the results that are published, that I know, are in terms of L3 norm of the pressure, so the integral square of the pressure in L3 being finite implied regularity. And there are results, again by Sergin and Sverak, about one side bounds for the pressure implying regularity. Now, negative, so the minimum of the pressure is a very important, and they will come back, an important, at least in compressible flows, a minimum of the pressure is a dangerous place. And this theorem makes perfect sense from that point of view. Also, when people are trying to do experiments and study actually vorticity stretching, they put bubbles or markers at regions of minimum pressure, and they're trying to follow them. It's not a Lagrangian tracer, though. So, as I said, the gradient in L3 is a quantity that I'm favoring now. And as you recall from the previous red line, it was known that the power 1 is integrable in time. And it is not known that the power 2 is integrable in time, and that would imply regularity. So, and this is similar to the condition, the Prodi-Serrin condition in terms of scaling of U in L infinity squared. Exactly the same scaling, but of course there is no implication. W1 3 is not embedded in L infinity, barely. So today I'm going to mention this theorem, that if you take the pressure representative and you assume that is continuous with values in L3 halves, then you have regularity. So I was surprised that I didn't see this in the literature. I think that maybe I didn't know to look. So what we don't use continuity. We need essentially uniform integrability of the integrand, the P3 halves. And notice that P3 halves is bounded by UL3 squared. So the pressure condition boundedness of L3 infinity implies boundedness, but the pressure condition would be stronger than requiring boundedness of the L3 norm, except we need more, we need continuity. And I don't know that how to prove, or if somebody did prove that L infinity here is enough. I have my little doubts, but yeah. Or on the other hand, continuity, you'll see it's not a big deal. So in terms of the structure functions, I have the following, and I want to mention a little bit here, the following result. First, let's understand what I call a structure function here is not the usual thing. I take the integral of the displacement squared on a ball of radius r, and I integrate against the singular kernel dy over y cube all the way to 0. So this, in some sense, is a tall order. But so for practitioners or people who do numerics, they pull this y cube outside and divide by r cube, and that's their average. And I don't think they would feel that's a big difference. For us, it's a very big difference. And I think this is the correct quantity. So this quantity requires a deeper understanding. So if you are assuming, as you will see below, what I'm going to require it to do, one way to guarantee this will be a very simple way in which it will, asking way too much, it will be some modulus of continuity in L3. If you would have a Dini modulus of continuity in L3, you would be okay. That's much more than what this is actually, much, much more. So this requires, here the requirement is a uniform integrability of this quantity. So, and not even that, it requires it to be small. So there is a delta, a measure size, so that if I can find one displacements, so imagine this R to be exactly LD or anything larger than LD, on which the property is that if I integrate on small sets of measure at most delta, I get the measure of viscosity. This is dimensionally correct. Those people who know me, you will know that I care about that. So if that would be the, unless I make mistakes, of course. So if this is smaller than the viscosity, then that means the Navier-Stokes solution is small. So this is a fixed constant, and so this would in particular happen if this object is small for small r. So if there is a modulus of continuity here, that's Dini integrable in L3. So then if I have a bound of this quantity by a constant of x times the integral of the modulus of continuity, then I have a constant here, and then if uniform constant, then I have uniform integrability. So it'll be an infinity. So the point is that that there is no such bound. So in addition, we could allow this to happen as a deteriorating rate, so smaller and smaller r required in order to do this, as long as the rate is integrable in time to some power larger than 4. And if you look at the classical LD, I'm going to come back to that classical LD, which has some formula. This is the same formula as before if you use the dissipation epsilon as being nu times gradient u squared. This is then nu to the minus 3/4 and times epsilon to 1/4. So then that is integrable to exactly 4. So I'm missing by a log or something. But there is an assumption here. So let's interpret this in terms of expected turbulent behavior, if you don't mind. So suppose that 2 is 2/3 for simplicity. So that turbulence tells me if I take an ensemble or an average or integrate with respect to some probability measure, this object that I defined, I get epsilon times r to 2/3. And then my requirement, well, my requirement is without the averages. It will happen with large probability, maybe with a bigger constant here. But if I integrate this right-hand side on A, I get epsilon to the power 3/2. I get epsilon r times the measure. And the condition will be satisfied if that integral is less than nu cube over 2. See, if you rearrange what that means, if you say, well, let's measure r. I didn't know what r is. I'm telling you what r is right now. I'm going to say, I'm going to pick r so that I get a small measure for A. So I can call the measure of A r cubed. Then here is an r4. And if you do the algebra, you get a constant multiple of the Kolmogorov dissipation scale. So this tells you this condition, if there is scaling of this sort, this condition is satisfied, and is satisfied at LD, the dissipation side. If you interpret turbulent behavior, then this implies regularity with large probability. This is not a shocker. Nobody in turbulence theory tells you that the Navier-Stokes solution is singular. They say the asymptotics are singular. That below the turbulence dissipation scale, you have nice behavior, and therefore this integral with y cubed there that I put there is finite. Okay? And quantitatively, this tells you that it is the correct one. Now let's go back and imagine a little bit what happened is r is larger, if the exponent here is larger than 2/3. If it's larger than 2/3, it tells you that this behavior happens already at larger scales. It's going to not be 1/4. So the LD will not be nu to 1 to minus 1 times 1. It will be larger scale. So you'll discover this at larger scales. So I'm going to chase, are there any questions so far? I'm going to talk a little bit about the Euler equations and then come back to this a little bit about the proof of this thing. So, the statement here is that I have a requirement of uniform absolute continuity, in other words, this integral to be smaller than some number, and this happens at scales that are small larger than the smallest scale. And larger than what scale? Well, larger than the dissipation scale if I have exactly Kolmogorov, and if not, larger than a larger dissipation scale. So formally, if you take viscosity to zero, you get the Euler equations, and this busy slides reminds you a little bit of notation about the Euler equations. I'm going to mention some results about the pressure and the Euler equations as well, and then come back to the pressure in Navier-Stokes. So this is the Lagrangian path. This is what Lagrangian means. Your time derivative of the Lagrangian path is the velocity. Material derivative is denoted like so. That's what material derivative does if you compose a function with Lagrangian path. The notation, by the way, I was mentioning, Vlad, that I started thinking about Euler with Sergio Kleinemann. This is Sergio's notation. So the symmetric part and antisymmetric part, the J is the antisymmetric part. So this is the rate of strain matrix, which is denoted S, and this is the action of this matrix is cross product with the vector V, so it's a vorticity. This is the vorticity equation because the gradient, the antisymmetric part annihilates the vorticity, it's cross product. So therefore only the symmetric part survives. So this is the vorticity equation. I will refer to this as the S equation, the equation for the rate of strain. You take the gradient and symmetric part. And J square, which is the square of this matrix, is negative, and it's proportional to projection perpendicular to the direction of vorticity. And capital P, again, Sergio's notation, is Hessian of pressure. So some of you know that if you look at the vorticity, there is a Pilkov-Omaida theorem that tells you that magnitude of vorticity controls blow up. So what we should actually look at is how the magnitude changes, and it has a rate of change that is given by some integral, and that integral depletes if the vector direction in it is canceling on small distances. And that was mentioned also in the talk by Yao this morning in the case of IPM and other equations. So you take the transport equation and you get a C that is the gradient perpendicular of the scalar. It's exactly like the vorticity, and you get cancellations of this sort. So if the matrix P, remember the minimum of the pressure kind of thing that as Kavriaz and that Sergin and Schwer talked about in visit equations, well, if they were compressible, the pressure would be a function of rho, and you would see that immediately at the danger of being at the minimum of pressure. So at the minimum, the Hessian is non-negative. So if that remains so in a weak vorticity region for some time, then there is blow up. So this is all the result, and I'll give you a simplified version. So if you mark a point and assume that there is a time on which the following properties hold, the vorticity does not blow up by then, is bounded, and the pressure Hessian remains non-negative on this particular path, this particular trajectory marked. In other words, the supremum is called capital omega, and the non-negativity is there, so it doesn't bother me. And we assume that initially the strain matrix is non-zero and somehow larger than omega. That's why I'm referred to vorticity as being weak vorticity. So in a weak vorticity, there are many examples in the 1D model that we all love. The vorticity, the blow up is happening near a place where the strain of matrix is non-zero and the vorticity is zero. So so that if that is the initial data, and the time of this situation is larger than the time omega, which is a non-dimensional quantity, is larger than the log of 1 over sigma 0 minus omega, then you have blow up. So in other words, you have the Hessian of the pressure does not oppose the blow up if it has a sign. And that means that the next result is a little surprising, which says that it's enough to control some magnitude of the Hessian of the pressure to avoid blowout. So this is a fancy quantity that is finite for sure. These are unit vectors, zeta and xi. And if the Hessian of the pressure is finite, L infinity, and all this is of course finite, and then the result in Dongo-Che says that there is no singularity. And in particular, if you are assuming the type 1 kind of blow up assumption that you are blowing up like t minus t, each derivative like t minus t, so two derivatives like t minus t squared, then if this prefactor is, this limit is less than 1, there is no blow up. So this part is the negative part, so only one sign matters. Then xi is the direction of vorticity, and zeta is the direction of the stretching of vorticity. So it's rather physical, actually. And these are the comments about L infinity implying this. And if L infinity, then there's no blow up. And okay, so I recall models. There is a classical model of VA force which tells you in the S equation model. The S equation has some known locality, and there is a model of mine in which you replace partial derivative, material derivative by prime derivative. So you take the S equation as it was. So if you replace this material derivative by partial derivative, you blow. And this is and VA force replaced this by an integral. Just the integral of, so make it trace 0. So 1/3 the integral of S squared. And then that was VA force and there was no J. So those blow up and they are misleading because in those cases, the pressure can be anything. And if the pressure is bounded, there is no blow up. Hessian of pressure. So there are localized versions. I don't want to talk about them. So but I'll show you the proof because it's elementary and nice. So if you take a second derivative of material derivative of omega, you get the Hessian of the pressure times omega. Why it's important and it's true. And then you take the magnitude of omega, its material derivative. Well, that's the same as taking the material derivative of S of omega and dot it into S of omega divided by S of omega, because that's the magnitude of dt omega. And therefore you get, using this equation, you get the equation about the magnitude. And in Lagrangian variables, you obtain, therefore, the same thing in Lagrangian variables, and you call this guy Q, okay? Q because he's Q. And then after that, you integrate in time, and you get a constant at time 0 minus the integral of Q omega. This is our criterion. At the end of the day, Q is the quantity whose sign we'll take to be 1, and then we are gonna, so I have this inequality that looks wrong, but it's right. And then you integrate this once, you get this information, and then you have a Gronal inequality that tells you that if I have a double, it's a double Gronal, right? Then you get this. So that's the whole proof. I think that, yeah, it's a little striking because if you look at the S equation, P square itself, so looks like cannot stop it, right? So let me just show it to you, then tells you again, why is it non-trivial or non, is that this guy alone, why is he stopping this guy? Okay, that's where the puzzle is. So this guy alone being bounded, why does he stop S square? Okay. It does because they're related, but okay. So now let's return to Navier-Stokes. So I'm belaboring this. We like the pressure. We have a representation of the pressure. You take spherical averages and you add to the pressure, the spherical average, so spherical average on the skin of the sphere, and you add to the longitudinal square velocity, and it solves an equation with an integral term in terms of the velocity itself, but it's a first order equation that you integrate from 0 to where you are. And that I call a monotonicity. Is not, it doesn't have a sign, but the reason why it is the monotonicity is that it controls this one locally with information that's local. So this W, you can decide on which vector independent on Xi you subtract. So you can take U of X, for instance, or 0. So this means that the pressure can be at any scale R represented in terms of a sum of two guys, where beta is an average. It's actually the average in R on two distances on the spherical average. And pi is what's left. So in particular, P minus beta vanishes for harmonic functions. So it's the anharmonic piece. So pi is an anharmonic piece. And beta obeys very good bounds. And I don't know if I wrote it right. So pi is an explicit expression in terms of squares. Pi vanishes quadratically. Here is the formula for beta. And I forgot to say it, but I'll say it again. It's very important. All the information you need is in the ball of radius 2r. You don't need to know farther away. So the pressure at any r is defined locally like this. And one guy is super, and the other guy is quote unquote small. So that's why I belabor this. I think it's important, and it might be important in many situations. It's a useful thing. Here is how I write down the pi. You don't really care, but the main point, I mean, it's not a unique way of doing it. The bounds for beta are remarkable. So remember, the pressure is 2 Rieses on u squared. So it's not true for the pressure that it's even bounded in L infinity if u is in L2. But beta is not only bounded, but it has, okay, it's bounded by L2 norm in L infinity. So you have this other bound which uses Hardy inequality. So this follows, is non-trivial, follows from a monotonicity lemma, and this one follows for Hardy. So we also, because beta is an average of P, and P has these bounds, beta has the same usual bounds based on the Ries transforms that are not exploding at r equals 0. And there is another bound that I'm going to use soon, so which is for beta in L3, that is technical. So, but the important thing here is that I cannot take 2. If I would take 2, I would get a bound in L3 here with just a pain, and it's not true. And it's unfortunate, but it's not true. All right, so should these bounds hold at any fixed r, we would have a regularity. I don't want to belabor that. So pi is bounded by the structure function. So that's why I have a theorem about approximate function, okay? So pi in LQ is bounded by r squared gradient u in L2Q, and that's why I like L3. So pi in L3 halves to 1/2, which is a natural viscosity kind of scaling object, is bounded by gradient u L3. And remember, the gradient u L3 is integrable. So this would be uniformly integrable if it was only one function. And in particular, if it was the time average, then it would be uniformly integrable. Okay, so this, for almost t, this is absolutely continuous with respect to Lebesgue measures. So the criterion says that if it happened uniformly in time, even with r depending on time, then the solution would be smooth. So that's the essence of this. So this is one way of writing the theorem. So you assume, which is an interesting way, I think, you take the pressure pi, the piece of the pressure that you don't know how to bound, and you restrict it to regions of exceedingly high velocity. And you assume that that happens for an R that you can, that restriction has small L3 halves measure. And then that R is integrable. Let's imagine that R is time independent, and then for sure, if R is integrable to a negative power, then the solution is smooth. And one way of generating this condition is by this uniform absolute continuity. Suppose there is an R of t like this one, and that you have absolute, well, the integral on sets of size delta, delta being small enough, are less than the viscosity. Then you have regularity. So how do you prove that? You prove that you bound L3. So you bound L3 in time, you write the equation that L3 in time, and then I'll give you one proof for that implies also that statement about continuity of pressure. You separate into regions of okay velocity and uncontrolled velocity. Velocity is very large. And then because of that, I'll skip over the, maybe I don't, so there is a bound for pi in the region that's good. And this is not optimal. I have a better way of dealing with. So the region that's bad, okay, so in the region that's good, we're okay, and the region that's bad, we do a little bit of interpolation. So we have this object that we have an assumption on it. This is really pi on the region where u is large. So then I have u dot grad u, and I use the fact that there is a dissipation in the Navier-Stokes, and let's call that dissipation d. And that d by some interpolation is larger than L9 to the third. So it's just Morray's inequality for 3 halves. So then you use that dissipation, interpolation straightforward, and you get that this guy can be, that's where you use the condition that the integral in 3 halves is smaller than the viscosity. Okay, so you have all the constants here come from interpolation. That's why I said the constant is determined universally. The other guy is interesting. So the other guy, you don't know, it could be dangerous. So you use this information about L3 of the other guy, hide again in the dissipation. And it is here that the power 4 enters in order to produce out of this guy a time integrable object. So then you get an ODE, and that's the end of the story. So if the pressure is, so the proof of the pressure continuous in time implied continuity of pressure implies continuity of the average, and therefore continuity of pi, and then the measure of the large region is small by energy, and therefore, if pi is continuous, the condition is satisfied with time independent R, because it's a compact path in L3 halves. Okay, so there are other kind of bounds that are interesting. So you can take other examples. So there is the Berselli-Galdi type, so L3 halves, bounds on pi imply regularity. And higher power in time, and lower power in space. 9/4 is also an interesting number, imply regularity. So I want to conclude with this. I want to say that there are hidden here 2 important quantities, the gradient u in L3 and u in L3. And u in L3 is a Reynolds number. So u in L3 divided by mu is a Reynolds number. And there is not giving you a scale. So it's a Reynolds number for R3 for essential, or in other words, a scale independent Reynolds number. Gradient u in L3, it's a velocity scale. It's a natural velocity scale. So I think that one should investigate the behavior of U divided by gradient U in L3 and do refined self-similarity for that. So the recap is here. The pressure continuous with values in L3 halves imply regularity. What I call the second structure function, which is with that definition with the integral all the way y cubed down to 0. That function in L3 halves is in L1 in time. But if it would be uniformly integrable at a small scale, then the solution would be smooth. And that's it. Thank you very much.
I was wondering, in practice, how much does pressure oscillate in
what?
In practice, in like numerical oscillations or in real flows? Does one see a lot of oscillation?
So this is fluctuating pressure. So there is the typical examples are, okay, so there are examples in which you have pressure-driven flows. It's a drop of pressure. Mm-hmm. And then there is oscillations around that. So that goes under acoustic waves. So they have a lot of information about oscillation of the pressure. So there is oscillation of pressure. Now I don't know quantitatively results about that. It's a good question. So the measuring pressure locally is probably difficult, except if you have a compressible effect in which you're listening to it. Mm-hmm. Mm-hmm.
So I may have missed the continuity of the pressure. There's some smallness you're using because if you use really continuity versus L infinity.
Continuity with values in L. So this continuity with values in L3 halves.
Yeah.
And no smallness in that. You're having a compact. You have a function in L3 halves. You take its L3 halves power. You have a function in L1. That's absolutely continuous. Now you have a path which is compact in L3 halves. That's absolutely continuous. Uniform, so you can break it into small pieces. You're right in some sense. You can break it, but because it's compact.
I see.
So small jumps would be also
what?
Small jumps would be also possible, right?
Well, if the small jumps are again commensurate to your desire. In this particular case, I have a finite desire. I have the desire nu. I don't have 0. So yes, I could actually envision a situation in which there are small jumps, so that the sum of the jumps is not new.
So if I understood properly, if you want to build blow up, you need to transport the pressure minimum for long enough time.
Yeah. Oh yeah, that's a theorem.
So in this Howell scenario, where is the pressure minimum happening? Where they have the anti-spin cylinders? I actually don't know.
Probably on the axis.
Is it on the axis?
You mean in the middle, on the axis of?
Because particles on the axis never leave the axis.
Yeah, but it's 0 probably. I don't.
No, but it's a minimum, right? So according to your theorem, if it's on the axis, you can blow up. But I don't think it's on the axis. Is it maybe on the plane where they spin the cylinders?
Good question. But at the singularity, I think there is actually like an increase in pressure, right?
I don't know. I'm asking.
So I don't know either, right?
There is a paper by about the pressure decomposition in
actually the guy. All right.
At the right. At the right. So the professor from Warwick.
Yes.
So what is the conclusion there?
I don't remember. But I think that the pressure is increased at the singularity. That was my impression.
It has to be at the singularity.
Yes.
Nowhere else could be. It's not at the axis. But
No, the axis.
it has to be at the singularity. Because it doesn't matter if it's in the interior, the cylinder or the exterior, so it makes no difference. The only important information is at the singularity. So it has to be at the singularity.
But the pressure minimum thing is on Navier-Stokes.
No, Euler. Euler.
But that was about the Hessian of the pressure. for Euler.
Yes, but the minimum has, as long as you keep the Hessian positive, you're happy. It doesn't have to be strictly positive. You have to stop bothering you.
I see.
So yeah, no, you're right. It cannot be at the axis. It'd be too good. Any other questions? And let's thank Peter again.